I welcome you all in this lecture of the ordinary differential equations. Today I am going to discuss the ordinary differential equations with constant coefficient having degree 1 and order 2 or more than 2. So a differential equation or linear differential equation of nth order is given by, say, your a naught dny upon dxn plus a1 plus a2, then finally we will have an into y equal to rx. So here the coefficients a0, a1, a2 and an are constants, where a0, a1 dot an are your constants. Now if we denote d by dx as capital D, the operator, then we will have a0 d power n into y, plus we will have a1 d power n minus 1 of y, plus a2 d power n minus 2, plus an of y equal to rx. Now this is your function of function of d, so we can write it as some function of d of y equal to rx. This is your linear differential equation of nth order with constant coefficient. Now the solution of 1 is given by the solution of 1 is your y equal to yc plus yp, where yc is the solution of the differential equation in which your right hand side is 0. That means when your rx is 0, and such type of differential equation are known as homogeneous differential equation. So yc is the solution of this differential equation, a0 d power n, a1 d power n minus 1 plus a2 d power n minus 2 plus an of y equal to 0. That means when your right hand side is 0, where y is the solution of this one, and it is known as complementary function. This is known as your complementary function, and yp is known as particular integral and your yp is equal to 1 upon fd of rx. This is the value of yp. I will discuss this yp in detail later on, but here you can see that your yp will be the 1 by fd of rx. Now what is your 1 by fd? I will discuss about it in detail. So let us discuss the complementary solution. Complementary function. Complementary function means it is the solution when your rx is 0. So consider the differential equation a0 d power n a1 d power n minus 1 plus a2 d power n minus 2 and then an of y equal to 0. And this is the differential equation when your right hand side is 0. Now suppose that its auxiliary solution is, let y equal to e power mx is the auxiliary solution of this equation. say this is equation number 2. Suppose that this is the auxiliary solution of 2. Now if it is solution of 2, then it must satisfy this equation. So your y means, let us operate this y, let us send this y inside the bracket, then we will have a and y. At here we will have dn n minus 2y, dn n minus 1y and dn y. dn y stands for the nth derivative of y. So from here your one time differentiation of y will be m e to the power mx, two time differentiation of y will be m square e to the power mx, and then your n time differentiation of y will be mn e to the power mx. So now if you put the value of y in equation number 2, hence by 2, your first term will be a naught, then the nth derivative of y is your m power n e to the power mx, then we will have a1. Now n minus 1th derivative will be m power n minus 1 e to the power mx, then your last term will be a and y is e to the power mx. Now let us take e to the power mx common. So if you take e to the power mx common, then we will have this term. Now as we know that e to the power mx cannot be 0, so e to the power mx cannot be 0 for positive values of m. So from here this equation is equal to 0. So this is equal to 0. Now if you compare this equation with your equation number 2, then you can see that in place of d, now we have small m. So this is known as auxiliary equation. This is known as your auxiliary equation, and you can see that in auxiliary equation we have small m in place of d. So you can say that this equation will be obtained when we replace our d by small m. This is known as auxiliary equation and can be obtained by replacing d by small m. So this is known as your auxiliary equation. Now as it has degree n, so obviously it will have n roots. Now let us discuss the nature of its roots, whether the roots are real or distinct, or complex conjugate and pure imaginary. So case 1, now because the degree of this equation is n, so it will have n roots. So let m equal to m1, m2 and mn. Suppose that these are n roots and all are real and distinct. Suppose that all are real and different one. So if these roots are real and distinct, then your CF will be, complementary function will be, you know that our auxiliary solution was e to the power mx. The initial guess solution was e to the power mx. Now if e to the power mx is the guess solution of this differential equation 2, then e to the power m1 x will be the solution. Similarly, e to the power m2 x will be the solution, and then e to the power mn x will be the solution. So as m1, m2, mn are the roots of this auxiliary equation, and our initial guess was e to the power mx is the solution of equation number 2. So if this is the solution of equation number 2, then e to the power m1 x will be the solution, e to the power m2 x will also be a solution, and e to the power mn x will be also a solution of equation number 2. And we know that by superposition principle, if y1, y2, yn are the solution of differential equation of nth order, then their linear combination is also solution. So using the superposition rule, our solution will be this one. So when your roots of the auxiliary equation are distinct and real, then this will be your complementary function. That means c1 into e to power m1x, where mn is the first root of the auxiliary equation, c2 into e to power m2x, and then cn into e to power mnx. Case 2. Suppose that two of the roots of auxiliary equation are equal. Say, this one is the particular case of this case. Suppose that two roots are equal and rest are distinct, and other roots are distinct. Say m1 and m2 are equal, and suppose that other roots are m3, m4 and mn. Now as two are equal, so in this case our CF will be, now if we put m1 equal to m2 here, then you can see that this will be a c1 e to power mx plus c2 e to power mx. Now if you take e to power mx common, then we will have c1 plus c2, and c1 plus c2 can be written as another constant a. But in that case, right now the order of the differential equation was n. So we must have n coefficients of integration. We should have n constants of integration. Now in case if your m1 equal to m2, then you can see that here we will have c1 e to power mx plus c2 e to power mx. Now if you take e to power mx common, then we will have c1 plus c2, and that is again a constant which can be written as some another constant a. So that means your one constant, now your one constant has been decreased. So to overcome this difficulty, let us assume the solution as c1 plus c2x, because we know that if e to power mx is a solution of some ordinary differential equation with constant coefficient, then x e to power mx will also be the solution of that differential equation. So here you can see that c1 e to power mx is the solution, and your x e to power mx will also be the solution of that differential equation. So in this case, our solution, when your two roots are equal, our solution will be c1 plus c2x. If you do not write x here, then this will become your c1 plus c2, and that will become your new constant, and that means you can see that one constant is less than n degree of the degree of this auxiliary equation. So that means we will have n minus 1 constant, and that is wrong. So here we will write x, and as all the roots, other roots are distinct, so our answer will be this one. So this is when your two roots of the auxiliary equation are equal. If three roots are equal, say their common value is m, and other roots are distinct, then your CF will be c1 plus c2x plus c3x square e to power mx, and then c4 e to power m4x, and then cn e to power mnx. So this is your answer. Now this is when your roots of the auxiliary equation are distinct. Now case 2, when roots of auxiliary equation are complex conjugate. When the roots of the auxiliary equation are imaginary. We know that the complex root occurs in conjugate. So if m equal to alpha plus I beta is the root of the auxiliary equation, then alpha minus I beta will also be the root of that equation. Suppose that the auxiliary equation has two complex conjugate roots and other roots are distinct. Or let us discuss a differential equation of order 2, then it will have two roots, say m equal to alpha plus I beta, m equal to alpha minus I beta. Now if the differential equation has order 2 and it has these two roots, then your CF will be, assuming that these two roots are distinct. So if these two roots are distinct, then our solution will be c1 e to power m1x plus c2 e to power m2x. If we assume these two roots are distinct, then CF will be c1 e to power m1x plus c2 e to the power m2x. Now let us simplify it. Here you can see that your e to the power alpha x will be common. So in the bracket we will have c1 e to the power I beta x plus c2 e to the power minus I beta x. And as e to the power I theta is cos theta plus I sin theta. So we have cos beta x minus I sin beta x. Now let us take the terms of cos and sin common. So we will have c1 plus c2 cos beta x. Then here we will have ic1 minus ic2 sin beta x. Now c1 plus c2 is constant, ic1 minus ic2 is constant. So you can write it as a cos alpha, a cos beta x plus b sin beta x. So this is the complementary function when you have two complex conjugate roots. So if we have complex roots, then your CF will be e to the power alpha x, where alpha is the real part of this root. So e to the power alpha x, then a cos beta. Beta means the coefficient of I. So we will have a cos beta x plus b sin beta x. So this is the solution. This is the value of complementary function when we have two complex conjugate roots. Now we can also rewrite it as, now suppose that if we write a as, say, some constant, if we write a as a into cos theta and b as a into sin theta, then this will be your cos a into cos b plus sin a into sin b, and that is your cos a plus b or cos a minus b. Or if you write a as a sin theta and b as a cos theta, then this will become your sin a cos b plus cos a sin b. So that means, or the same formula can be written as e to the power alpha x. If you write a as, if you write capital A is constant, so we can write it anything. So if you write capital A as capital A into sin alpha, or you can say that some constant. If you write a as, say, a into sin c, c is constant, and b as a into cos c, then this will be your, then you can see that this is your, here this will be your a sin c and this b is your a cos c. So that means sin a cos b plus cos a sin b. Then this will become your, if you take a common, then this in the bracket we will have sin a into cos b plus cos a into sin b. That means sin a plus b. So that means in this case your solution will be a into e to the power alpha x sin beta x plus some another constant, say b. This is also your CF, or if you write it as a cos beta or a cos c, b as minus a sin c, then your CF will be cos a cos b minus sin a sin b, that will be a cos a plus b. So we have these two formulae, another formula for the complementary function when your roots of the auxiliary equation are complex conjugate. Now suppose that if roots occur in pair, if we have a double root, so if suppose that m equal to alpha plus I beta and alpha minus I beta occurs in double, suppose that this root is repeated. If this root is repeated, say in double, you can see that we have four roots right now. One is alpha plus I beta, another is alpha minus I beta, and again these two roots repeated. So in this case your CF will be, I am starting with the first one. The first formula was e to the power alpha x a cos beta x. Now a can be written as your c1 plus c2x cos beta x, and b can be written as your c2 plus c3x, c3 plus c4x sin beta x. So if roots of auxiliary equation are distinct, if the roots of auxiliary equation are conjugate and occur in double, then this will be your C1, where we have written C1 as C1 plus C2x. If these roots occur in triple, or if these two roots occur in 3 times, so then we will have C1 plus C2x plus 3x square cos beta x plus C4 C5x C6 x square sin beta x. So this is your complementary.